Good day, everyone. This is Dr. Soper here, and today I'll be discussing the 11th topic in our series of lessons on information privacy and security, with today's topic focusing on denial of service and intrusion detection. One of the commonest and most visible types of attacks that malicious parties carry out against networks is known as a denial of service or DOS attack. Recalling that information security is focused on the CIA triad, that is, confidentiality, integrity, and availability, we can better understand how denial of service attacks fit into the broader panoply of threats against information assets. Namely, a denial of service attack is an attack that seeks to negatively impact the availability of network resources. Availability refers to the ability of an authenticated user to access authorized information assets in a quick and efficient manner. With this in mind, it is important to understand that availability is not a binary true-false concept. On the contrary, availability comes in degrees, and as such, information assets cannot simply be classified as available or unavailable, but can also be considered to be partially available. Because of this, a denial of service attack does not necessarily need to fully disrupt the availability of information assets in order to be successful. Simply slowing the performance of a network to a point which causes consternation for users is often sufficient for a malicious party to claim victory. Denial of service attacks can be initiated in many different ways. First, a malicious party might cause a transmission failure by physically severing or otherwise interfering with the connection between an information asset and a legitimate user. Alternatively, a malicious party might physically sever or otherwise interfere with the intermediary systems or connections between an information asset and a legitimate user. The second way in which a denial of service attack can be initiated is through traffic redirection. In this type of denial of service attack, a malicious party manipulates a router's routing table such that either no network traffic is directed to the router or an excessively large volume of traffic is directed to the router, thus disrupting the normal flow of information across the network. Third, a malicious party can initiate a denial of service attack by targeting a domain name server, or DNS. Domain name servers are a critical component of the Internet infrastructure because they translate textual web addresses, such as google.com, to their appropriate numerical IP addresses. A malicious party who is able to alter a domain name server's lookup table can therefore cause traffic to be incorrectly directed either toward or away from the target server, thereby disrupting service. Finally, a malicious party can initiate a denial of service attack by performing connection flooding. Every communications channel has an upper limit on the amount of information it can carry. Similarly, every node on a network has an upper limit on how much data it can process. Flooding a network with so much information that either of these limits is met or nearly met will bring the network to a grinding halt, or at least to a slow crawl, thus disrupting the availability of information assets. A connection flooding attack seeks to negatively affect the availability of a network resource by exhausting or overwhelming the capacity of a communications channel. Connection flooding is the most elementary type of denial of service attack and is also often the simplest form of DOS attack to actually implement. The figure shown here illustrates the generic principles underlying the various types of connection flooding attacks. As shown in the figure, the communications link, which connects the target server to the rest of the network, has a maximum information carrying capacity. Similarly, the server itself has a maximum information processing capacity. Generally speaking, a connection flooding attack works by simply overwhelming the communications channel or the server by sending it more requests than it is physically or computationally capable of handling. With so many malicious requests being directed toward the server, requests from legitimate users cannot be handled in a timely fashion, if at all. Although the general principle underlying a connection flooding attack is quite straightforward, clever malicious parties have developed many different types of connection flooding attacks, each with its own specific characteristics, strategy, nuances, and method of implementation. 5 of the most interesting types of connection flooding attacks include the echo chargen attack, whose name is derived from the character generator protocol, the ping of death attack, the smurf attack, the sin flood attack, and the teardrop attack. An echo chargen attack capitalizes on the echo command within the character generator protocol. The character generator protocol is a component of the broader Internet protocol suite and is designed to support efforts aimed at debugging, testing, and evaluating the performance of Internet connections. The echo command simply instructs the target server to send an identical copy of the data it has received back to the source server. An echo chargen attack, then, is characterized by a malicious party sending a large stream of echo request packets to the target server. Per the protocol, the target server will then echo those packets back across the network. If the malicious party has greater network bandwidth than is available to the target server and is able to flood the target server with an endless series of echo requests, then all of the target server's available network capacity will soon be consumed with echo requests and replies, thus disrupting the ability of legitimate users to access network resources. The ping of death attack is very similar to the echo chargen attack, except that it relies upon the ping utility. The ping utility was created as a tool for diagnosing and solving problems with connections between hosts on a network that relies upon Internet protocol addressing. Specifically, the ping utility uses the Internet Control Message Protocol to send echo request packets to a target server which, according to the design of the protocol, dutifully replies to the remote request. The ping utility then measures the round-trip time for each packet and tracks any instances of packet loss. Similar to an echo chargen attack, a ping of death attack is characterized by a malicious party sending an excessively large number of ping requests to the target server, which will attempt to respond to the requests. If a sufficiently large number of ping requests are sent to the target server, then the incoming ping requests and the outgoing ping replies will consume all of the server's available network capacity, thus disrupting the ability of legitimate users to access network resources. In principle, a smurf attack is similar to an echo chargen or a ping of death attack in that it seeks to bombard a target server with an overwhelming flood of data. A standard echo chargen or ping of death attack, however, generally requires a malicious party to have a great deal of bandwidth if the attack is to be successful. By contrast, a malicious party who successfully carries out a smurf attack can cripple or disable the target network even if she personally has very little bandwidth. In a smurf attack, a malicious party sends a ping request to the IP broadcast address of a large network. Because the ping request is sent to the network's broadcast address, the request will be relayed to every host on the network. Each of these hosts will, by default, then reply to the ping request. Under normal circumstances, all of these ping replies would be sent back to the malicious party. In a smurf attack, however, the malicious party intentionally modifies her ping request such that the address of the target server is specified as the source of the request. Upon receiving the artificially manipulated ping request, all of the hosts on the network will therefore send their ping replies to the target server, thus overwhelming its capacity and disrupting the ability of legitimate users to access network resources. The usual way in which legitimate users establish a TCP connection with a remote server is by conducting a TCP three-way handshake operation. As the name suggests, a three-way handshake involves three steps. First, the user sends a SYN or synchronize message to the remote server in order to request a connection. The server then replies to the user with a SYN-ACK or synchronize acknowledge message in order to indicate its willingness to establish a connection. Finally, the user responds to the server with an ACK or acknowledge message, after which the TCP connection is established. Since packets must flow back and forth across the internet between the user and the server, completing a TCP three-way handshake takes time. For this reason, servers maintain a SYN received or synchronize received queue. When an initial synchronized message arrives from the user, the server sends its synchronize acknowledge reply and adds the request to the synchronize received queue. When the user's acknowledge message arrives, it is matched with the original request in the queue, after which the request is removed from the queue and the connection is established. The synchronized received queue will retain requests for a period of time in order to allow users to send an acknowledge message back across the internet. The synchronized received queue, of course, has a maximum capacity and can only hold so many unacknowledged connection requests. In a SYN flood attack, a malicious party sends a large number of synchronized requests to the target server, which then dutifully replies by sending synchronized acknowledge responses, after which it adds each request to its synchronized received queue. The malicious party, however, never replies with the expected acknowledge message, and as such, the server's synchronized received queue rapidly fills with unacknowledged connection requests. When the queue becomes full, the server is not able to entertain any connection requests from legitimate users, thus disrupting the ability of those users to access network resources. In ordinary network communications across the internet, messages between users and remote servers are broken apart into segments of various lengths, which are then sent independently over the network. Because of the nature of network communications, these segments often arrive out of order. The server must therefore collect and hold incoming segments until they have all arrived, after which the complete message can be reassembled. In a teardrop attack, a malicious party manipulates the segments of a message such that they overlap or contain excessive payload data. When the artificially manipulated segments arrive at the target server, the server becomes confused because it is unable to find a logical way of reassembling the incoming message. If the server is not intentionally designed to handle the situation, the teardrop attack can cause the server to crash, thus disrupting the ability of legitimate users to access network resources. In a distributed denial of service, or DDoS attack, many different machines, often numbering in the thousands or tens of thousands, are used in an effort to disable or cripple a target server or network. Prior to launching the attack itself, a malicious party will use any convenient method to distribute a Trojan horse to as many target machines as possible. Each of these target machines then becomes a zombie and can be controlled remotely by the malicious party. After choosing a target, a malicious party transmits the messages to each zombie machine, instructing it to initiate the attack. The Trojan horse on each zombie machine then launches one or more varieties of a denial of service attack on the target server or network. If a sufficiently large number of zombie machines and a sufficiently large variety of denial of service techniques are used in the commission of a distributed denial of service attack, then the attack will generally be quite successful. The reason for this is that with many machines attacking the target from potentially all over the world using a variety of techniques, it becomes very difficult for security personnel to distinguish and isolate attackers from legitimate users. In the medical world, it is better to prevent a person from getting a disease than it is to treat the person after they already have the disease. In the world of information security, it is similarly better to prevent an attack than it is to detect the attack after it has already succeeded. Unfortunately, not every attack on information assets can be prevented, and for this reason, information security personnel can implement an intrusion detection system. An intrusion detection system, or IDS, is a device that monitors system activities with a view toward detecting malicious or suspicious actions or events. Specifically, intrusion detection systems can be used to detect two broad types of undesirable activities, namely, outsiders who are attempting to break into a system, or insiders who are attempting to perform inappropriate actions. Note that with respect to this latter point, insiders may be performing inappropriate actions either intentionally or unintentionally. In order to better understand intrusion detection systems, we must first become familiar with the terminology that is commonly used in discussions of such systems. One of the common terms that is associated with the use of intrusion detection systems is an anomaly. In the context of intrusion detection systems, an anomaly refers to abnormal or unusual behavior that is occurring on the network. Next, in the context of intrusion detection systems, misuse is a term that refers to an activity which violates the network or system security policy. As applied to intrusion detection systems, the term intrusion refers to a situation in which the system or network is being misused, either by outsiders or by insiders. When an intrusion occurs, security personnel may perform an audit in which the activities or actions of a user or the system are evaluated and analyzed. Finally, the use of intrusion detection systems commonly involves profiling, which refers to the process of observing legitimate users or the system in order to establish a model of what constitutes normal behavior. One way of understanding and classifying intrusion detection systems is by considering their scope. Broadly speaking, intrusion detection systems can be classified either as host-based systems or as network-based systems. An intrusion detection system can be considered host-based if it runs on a host on the network and is responsible only for monitoring activities on that host. By contrast, an intrusion detection system can be considered network-based if it is an independent, standalone device that is connected to the network, as opposed to host-based intrusion detection systems which monitor activities only on the host on which they are installed. A network-based intrusion detection system monitors activities on an entire network or subnet. In addition to classifying intrusion detection systems according to their scope, such systems can also be classified according to their mode of operation. Specifically, an intrusion detection system might be anomaly-based, signature-based, heuristic-based, or it might use a hybrid approach. An anomaly-based intrusion detection system works by allowing only acceptable activities or behavior. For this purpose, anomaly-based intrusion detection systems rely upon models of what is considered to be acceptable behavior. Whenever behavior is detected that is considered unacceptable, the intrusion detection system will raise an alarm. A signature-based intrusion detection system works by looking for known types of attacks. Just as with viruses, each known type of attack has a signature. To detect an attack, the intrusion detection system compares current activities against known attack signatures. The problem with such an approach, of course, is that new attacks, which have unknown signatures, will not be detected. In an heuristic-based intrusion detection system, the system automatically constructs and refines models of what is considered to be normal behavior. Attacks are then detected by comparing current activities with what is considered to be normal. Finally, a hybrid intrusion detection system is simply an intrusion detection system that combines two or more of the approaches used by anomaly, signature, or heuristic-based systems. The variety of intrusion detection systems can perhaps best be understood by using a 4x2 matrix, such as that shown in this figure. The four different modes of operation that an intrusion detection system might employ are listed along the horizontal axis, while the two different types of scope are listed along the vertical axis. With this framework in place, we can easily classify any intrusion detection system. Specifically, an intrusion detection system might reside on a host and use anomaly-based, signature-based, heuristic-based, or hybrid approaches for detecting unusual activity on the host. Alternatively, an intrusion detection system might reside on a network and use anomaly-based, signature-based, heuristic-based, or hybrid approaches for detecting unusual activity on the network. When thinking about intrusion detection systems, it is important to realize that such systems have two primary goals. The first of these goals is to correctly detect all attacks. Note that the system can make two different types of errors in its efforts to detect attacks, namely false positives and false negatives. A false positive can be thought of as a false alarm. An intrusion detection system makes this kind of mistake when the network is not actually under attack, but the system nevertheless believes that an attack is underway. Note that false alarms are annoying to both users and security personnel alike. A false negative, by contrast, occurs when an attack is genuinely underway, but the intrusion detection system fails to detect the attack. The second primary goal for intrusion detection systems is to perform their tasks diligently and effectively while consuming the smallest quantity of system resources possible and not causing any notable degradation in system or network performance. Unfortunately, these objectives often conflict with each other or are otherwise difficult to achieve. When an intrusion detection system determines that an attack is underway, it can respond to the attack in one of three different ways. First, the intrusion detection system might simply monitor the attack and collect data as the attack unfolds. This response is invisible to the attacker and can be used for attacks that are likely to have only a modest impact on the system. The information gathered about the attack can then be analyzed and used to strengthen system security. Next, an intrusion detection system might respond to an attack by automatically attempting to protect information assets. Examples of such a response might be to immediately disconnect critical databases or block all access to critical files. Note that these responses are often very visible to the attacker. Finally, an intrusion detection system can be designed to respond to an attack simply by alerting human security personnel. If an attack has the potential to cause a great deal of damage, then the best strategy is often to alert a human being who can make decisions about the situation and respond to the attack as it unfolds. Since human beings often take a comparatively long time to respond, the intrusion detection system may also perform some automated tasks, such as protecting critical files or other information assets, until human security personnel can arrive and take command of the situation. Well, my friends, thus ends our overview of denial of service and intrusion detection. I hope that you learned something interesting in this lesson, and until next time, have a great day.